Welcome back, my fellow organic chemistry enthusiasts. Today we will explore the chemistry of a tree that can survive atomic bombs and is nowadays commercialized on a billion-dollar scale as a dubious health supplement. We're talking about the molecule Bilobalide. Its characteristic features are a tetracyclic framework, numerous hydroxyl and lactone groups, and a terp-butyl group which actually occurs quite rarely in nature. To date, 3 complete syntheses have been published, and we will deep dive into these later in the video. They get shorter and more elegant, so this will offer a nice opportunity for us to see how organic chemistry evolved over the years and also to further test our scientific understanding. The syntheses get better as the video progresses, so make sure to stick around. If you're a full-blown synthesis nerd, I'm sure you will appreciate and understand the syntheses in their complete beauty. This video will also be informative if you have just some degree of organic chemistry knowledge, as many chemical reactions and reactivities are quite straightforward. If you're more of a normie and just interested in psychedelics, you are still invited to join the ride and tune out once things get too complex for you. In any case, I would highly appreciate it if you could subscribe to the channel, like the video and share a comment. These videos take a crazy amount of time to create, so I'm happy for all the support. So, bilobalide, what is it? It's one of the terpenoid natural products found in the Ginkgo biloba tree and was structurally characterized first in 1971. There are some interesting facts I wanted to share around the Ginkgo tree itself. Ginkgo biloba is one of the world's oldest living tree species. There are fossils very related to the modern Ginkgo that date back 270 million years, making it a living fossil. The name Ginkgo is the result of a spelling error of the German botanist Engelbert Kämpfer from around 1700. It should actually be pronounced more as Ginkgo, but Engelbert misspelled it as Ginkgo, and this name has prevailed in the West ever since. Ginkgo trees are also very resilient. They have survived the Great Kanto earthquake in 1923 in Japan and also the atomic bombing in Hiroshima. While buildings were irreparably damaged, Ginkgo trees were badly burned but miraculously survived and regrew with time. A quick Google search shows that Ginkgo biloba extracts are sold by everyone and their mother as a health supplement. It's a yellow brownish powder and is composed of around 5% terpene lactones, so bilobalide and other terpenes that we will look at later, and around 25% flavonoids, which is another class of natural products. This market is quite insane. Some reports estimate global sales of over $1.5 billion of Ginkgo biloba extracts. Ginkgo has been used in traditional Chinese medicine for centuries, so this is why millions of people are resorting to Ginkgo extracts today. They are often marketed for cognitive function, although there is no evidence for efficacy in healthy people. There have been some systematic reviews that show there are some effects for peripheral vascular disease and age-related macular degeneration, among others, but treatment of other conditions like stroke recovery or Alzheimer's disease is actually not backed up. Even though some in vitro and some in vivo studies suggest Ginkgo biloba has cancer preventive properties, large-scale reviews do not support this, and there even was a study that concluded that Ginkgo extract actually caused cancer in mice. This study is disputed though, as the extract they used was not representable. Instead of the 5% terpenes and 25% flavonoids, their sample contained 15% of terpenes and 30% of flavonoids. By now it's clear that Ginkgo has some significant impact on biochemistry and the physiology. As mentioned already, Ginkgo, like any other plant or tree, contains dozens of other phytochemical compounds. Quite unoriginally, some of them are called ginkgolides, which are structurally very similar to bilobalide but a bit more complex. These ginkgolide boys are actually quite ridiculous as they impact a whole bunch of biochemistry and have been explored through some structure-activity relationship studies, which are always very interesting. These are studies where you add, modify or remove functional groups and figure out what happens to the molecule's pharmacological activity. Ginkgolides are most often cited as agonists of a certain G-protein coupled receptor, the platylae activating factor receptor. PAF is a ubiquitous phospholipid involved in a wide variety of inflammatory and immunological disorders and pathways. Through this mechanism and also others, the ginkgolides can impact a long laundry list of biochemical agents. You have kinases and AMP, cytokines, interleukins, nuclear factor kappa beta, TNF alpha, COX2, LDL, proteases. just to mention a few of them. In contrast to ginkgolides, bilobalide does not affect PAF receptors. It does, however, show some other interesting biological properties, such as improving learning and memory in model mice with Down syndrome. This is proposed to arise from antagonism of GABA receptors that are a critical component of the nervous system. Unlike other GABA antagonists, bilobalide is not toxic and could thus have a selective effect for different indications. All these biochemical effects sound great and promising, but admittedly, research on biochemical effects and the mechanism of Ginkgo biloba is still at a very early stage. This is where organic chemistry can add value, providing reliable and flexible access to targets and also analogs, and fueling structure-activity relationship studies. It's also nice to not have a cocktail of compounds like in Ginkgo biloba extracts, knowing how much of which compound you are actually using in your assay. Let's move to the fun part now, the organic chemistry. We will not go into the detailed rationale of each retrosynthesis, so the synthetic plan, as this would explode the scope of this video. By studying the free syntheses in the forward sense, however, you will automatically understand which bonds were disconnected in which order and why. In such a complex molecule, there are of course hundreds of ways to plan a retrosynthesis. The teams of scientists involved only found their successful approaches through lots of hard work and numerous other conceivable routes. As always, the PhD students and postdocs involved deserve the most credit. We will start with the first bilobalide synthesis from 1987, published by one of the OGs in chemistry, Professor E.J. Corey and his PhD student Wei Guo Su. They started from this diester that underwent a base-mediated annulation with this propiolate. The reaction proceeds via the acylated intermediate that probably undergoes intramolecular electron transfer and forms a 5-membered ring. This 5-membered ring is part of the final bilobalide. As a next step, the enone was reduced to the allylic alcohol using sodium borohydride. This is selective and does not touch the two ester groups. Through ozonolysis and reductive workup, the 6-membered ring was fragmented into the dialdehyde. But because we have the free allylic alcohol, we conveniently form another 5-membered ring that we need as a hemiacetal. Then they protected both groups as methylacetals. Next, the team converted the two esters into aldehydes. You might know that stopping reductions of esters at the aldehyde stage is quite tricky. It can be done, but usually it's easier to just reduce the esters to the alcohols and then oxidize them back up to the aldehyde stage. Even though Corey's synthesis is a bit long, it's also very elegant, because if you tickle this intermediate with some acid, two 5-membered rings are formed in one step due to kind of a domino acetalization. This cyclic hemiacetal is also called a lactol group. Without further purification, they oxidized the lactol to the lactone with PDC, so even though they had to play around with oxidation states and close two rings, they end up with 80% yield over 4 steps, which is really nice. Next, they converted the upper acetal into the hemiacetal. This works selectively because the lactone and the tetrahydrofuran ring are opened up under basic conditions, and after acidification, the hemiacetal with a free hydroxyl group is obtained. You can take a moment to think about the mechanism if it's not clear to you. The new hydroxyl group was then methylated and eliminated. The team did this as they needed a way to introduce additional functionality because bilobalide contains an alpha hydroxylactone at this part. To introduce the rest of the oxygen atoms, they epoxidated both double bonds. Under mild acidic aqueous conditions, they then selectively opened the electronically more activated epoxide, affording a diol, which they also acetylated. Then, the acetal that was so far just chilling around was oxidized. By addition of boron trifluoride as a Lewis acid, MCPBA as a peroxy acid can add and fragment the starting material to give the lactone. Their attention then turned to the final ring. Under acidic conditions, they revealed the lactol and oxidized it with PDC to the lactone. Unfortunately, reducing the epoxide to directly afford bilobalide did not work out. Instead, they first deoxygenated the epoxide, which is basically the inverse of an epoxidation reaction. In a 2-step sequence, they did a dihydroxylation with osmium tetroxide and functionalized the sterically more accessible alcohol to the oxalate. Radical reduction with tributyl tin hydride then successfully removed the CO bond that they were trying to get rid of. Finally, after deprotection of the acetate, they completed the first synthesis of bilobalide. So, this was a bit lengthy and contained many redox manipulations, but it is impressive nevertheless. Through clever design and incorporation of functional groups with oxygens at the right time, Corey and Wei Guo managed to deal with the molecular complexity quite well. So, how did Crimmins and colleagues add on this a couple of years later? They kicked things off from this aldehyde that's a bit simpler than Corey's starting material, but it already contains one of the furan rings. Through nucleophilic addition and oxidation, they introduced the characteristic terbutyl group quite early in the route. Another nucleophilic addition of the acetonitrile anion gave a tertiary alcohol. Subsequently, the nitrile group that was just introduced was reduced with diol to the aldehyde. This set the stage for a third nucleophilic addition of this lithium enolate. Interestingly, the addition is very diastereoselective on one center. This happens because coordination to lithium positions the molecule in a quasi-six-membered ring that shields nucleophilic attack from one side. In the alternative chair conformation that might shield the opposite side, the terbutyl group is not positioned equatorially, so that one is not favored. Next, the silyl enol ether in the newly introduced 5-membered ring was deprotected with potassium fluoride. This favors enolization of the other ketone because 1,2-diketo compounds are not that happy. This enol was protected with pivalloyl chloride. In a second step, they also protected the secondary alcohol with TMS chloride. Of course, the secondary alcohol is much more reactive than the tertiary one. We can redraw this intermediate to help us understand the next step a bit better. A 2+2 photo addition between the two alkenes. This effectively creates two new rings, a 4-membered ring and a 5-membered ring. This reaction again is very diastereoselective, meaning that both the CO and the CH bond are looking up. This can be rationalized by this transition state here where again, the equatorial position of the terbutyl group contributes to the diastereoselectivity of the reaction. Some 6 years later when Crimmins and his team synthesized Ginkgolide B, one of the Ginkgolide boys we talked about earlier, they employed a similar 2+2 addition to forge a 4-membered ring. Supposedly this proceeds in quantitative, so almost 100% yield, which sounds crazy but let's just believe it. The cyclobutane actually contains all carbon atoms of one of the central furan rings, so this is why this reaction is so powerful. Back to bilobalide, they then proceeded with some functionalizations to build up the complexity. First, the ketone was hydroxylated in the alpha position. Then, they reacted the hydroxyketone with lead acetate, which cleaved the ring not symmetrically like an ozonolysis, rather it gave the aldehyde and the methyl ester. With some acid, the TMS group can be removed and the free alcohol forms an acetal with this aldehyde and methanol. This reactivity we know very well from Corey's work. They then reduced both esters, so the methyl ester and the pivalloyl ester, and again used lead acetate to cleave this diol. The terminal alcohol flies away while we are left with the ketone. You might wonder why they did these last few steps. The purpose of the sequence was to set the stage for the pivotal Baeyer-Villiger oxidation, which transforms cyclic ketones into esters. This is what's needed to introduce the oxygen atom that's missing currently in the cyclobutane. They assumed that this would be quite straightforward because they initially had embarked on a first synthetic route that used a slightly different starting material epoxide, and in this setup hydrogen peroxide gave the desired Baeyer-Villiger product in very good yield. You see here, and you might know already, that there are two potential products in Baeyer-Villiger rearrangements. To recap this, let's look at the mechanism. First, the carbonyl is protonated and attacked by the peroxide. Then, the resulting alcohol can push back an electron pair and migration of one of the two alkyl rests kicks out the hydroxide. This is a net oxidation because you form a carbon-oxygen bond to reduce peroxide to hydroxide. The catch is that ketones have two alkyl substituents, and both can in theory migrate to kick out hydroxide. Usually, tertiary rests are more likely to migrate because in the transition state, the carbon center of the migrating rest has some cationic character, and tertiary carbocations are more stable than secondary ones. In the case of the first generation synthesis, however, the secondary rest migrates because that one is electronically more activated due to the furan oxygen. So of course the team tried the same conditions, and of course it didn't work out. For some reason the starting material with a hydroxyl instead of the epoxide exclusively drove the undesired migration. Amazingly, however, using MCPBA as an oxidant inverts the selectivity. The The researchers figured that perhaps stereoelectronic factors were overriding electronic preferences. So MCPBA as a more electrophilic reagent than hydrogen peroxide might have favored migration based on purely electronic factors. To conclude the synthesis, they first oxidized the acetal and second epoxidated the alkene. Another dash of Jones reagent opened the epoxide and oxidized the lactol group. I think overall they lucked out big time on the Baeyer-Williger reaction. Of course it's bad luck that the first generation conditions did not work out, but it was also a lot of luck to have a workaround with over 90% yield. They obviously met the roadblock in their first generation route, which was opening of the epoxide, but if their second generation route got stuck at an earlier stage already as well, their entire 2+2 approach might have been fruitless. Such is the life of an experimental chemist. Overall, Crimmins synthesis is a bit shorter than Corey's and employs a nice cycle addition to build the tetracycle. However, it still relies on a lot of functional group manipulations and oxidations. So what did the third team, led by Ohtawa and Shenvi, do? You would think that if someone is revisiting a molecule 25 years after it has been synthesized multiple times already, they better have a super good idea. Their realization was that without the C10 hydroxyl group, Bilobalide is very symmetrical. Maybe they could leverage a symmetrical intermediate to simplify things. Instead of building up bilobalide from a long linear sequence and iteratively changing oxidation states like Corey and Crimmins before them, Ohtawa and Shenvi dared to rely on a late-stage hydroxylation to distinguish the quite similar lactones and to make things more efficient. This seems very risky, but let's see how it played out. Their synthesis started from this diester, which underwent an enantioselective Reformatsky reaction with this aldehyde. This is the first example of a catalytic enantioselective zinc Reformatsky reaction with a branched nucleophile, and it works with quite a simple bisoxazoline ligand to give great EE. Next, they subjected the product, which contains an alkenyl bromide, to radical conditions which led to a 5-exo trig cyclization. This reaction proceeded with a very high diastereoselectivity, which can be rationalized by looking at the 5-membered ring transition states. The preferred transition state has the acetal and the ester substituents quite distant from the other axial ester and thus minimizes 1 to allylic strain present in the other transition state. Now, they focused on installing the hindered tertiary hydroxyl group. You will remember that Corey did this at a very late stage via dihydroxylation, and Crimmins did it via addition of that acetonitrile anion onto a ketone. Instead, the team used the Mukayama reaction and employed an alkoxysilane as a reagent. This is unusual, but such species are often the active reductants in Mukayama reactions and are formed in situ through silane alcoholysis. Whereas standard conditions are limited to alcohols as solvents, using this reagent allowed them to conduct the reaction in a more apolar solvent like methyl cyclohexane. In methyl cyclohexane, hydration from the desired phase is preferred due to an intramolecular hydrogen bond that is reinforced in apolar solvents. The undesired diastereomer looks a bit different as it forms a lactone, but it corresponds to just dehydration from the other phase. At this point, the team wanted to install the quaternary center at C5, but most alkylation conditions gave the wrong selectivity or dehydrated the starting material. However, they observed that under acidic conditions, a quite stable oxetane is formed between the tertiary hydroxyl and the acetal. Because they could only carry forward one of the diastereomers here, they designed a clever diastereoselective reaction by using a chiral binol phosphoric acid. They then oxidized the secondary alcohol with IBX to prepare functionalization at C5. The team reacted the beta-keto ester with TMS-EBX, which is an alkyne transfer reagent. The oxetane group was key as it sterically shielded one of the phases. Performing this alkynylation without the oxetane resulted in the wrong diastereomer. Also, they had to have only one of the oxetanes because the other isomer decomposed, so this is why they had to use the chiral phosphoric acid earlier. They then reduced the ketone with samarium iodide. The diastereoselectivity here is quite interesting because it actually favors addition from the highly congested phase. And indeed, all other hydride reagents gave the wrong diastereomer. The preference for samarium iodide might be rationalized through chelation of samarium to the oxetane oxygen. Next, they wanted to convert the alkyne group to the lactone present in bilobalide. Standard conditions for anti-Markovnikov hydration of the alkyne did not work out, so they just invented a new methodology. Addition of base and trimethyl borate forms an alkenyl borate intermediate which can be oxidized with MCPBA to give a mixed anhydride or maybe even a ketene. Whatever the intermediate is, it's intercepted by the alcohol intramolecularly to form the lactone. So you've probably been wondering how they will transform this intermediate into bilobalide. Actually, it's quite simple, as hydrogenation and acidic hydrolysis removed all protecting groups and forms all lactones. Let's look at it step by step. The esters and alcohols are deprotected first. After redrawing this intermediate, it becomes clearer that the hydrated aldehyde can form 2 lactones and deliver the pre-final product. This multi-step reaction proceeds in high yield. At this point, the team had established a very elegant sequence of only 10 steps to arrive here. All they had to do was selectively functionalize the correct lactone. The problem was that this inner lactone is sterically hindered, lowering its reactivity compared to the outer lactone. For example, treatment of that pre-final product with KHMDS and the Davis oxaziridine exclusively hydroxylated the outer lactone and did not form any bilobalide. After some experimentation, they observed that, for example, addition of 1 equivalent of KHMDS caused full mass recovery of the rearranged isobilobalide skeleton. This is the result of a translactonization with the tertiary alcohol that changes the exposure and orientation of the inner lactone protons. The authors called this inside-out unfolding. Due to this isomerization, the inner lactone is sterically more poised to deprotonate. But is it enough? Well, when they tried this sequence with the normal isobilobalide with a free alcohol or the corresponding TBS ether, they observed only minor bilobalide formation. Conversion to the isobilobalide with a benzoate, however, gave bilobalide after deprotonation oxidation in 91% yield based on conversion of the starting material. Let's look at this finding in more detail. The first step in both of these scenarios is rearrangement to the isobilobalide skeleton as explained earlier. Under the conditions, the secondary alcohol is converted to its benzoate. This allows the inner lactone to be selectively deprotonated and oxidized to give bilobalide. This selectivity could arise from electronic activation, as the electron withdrawing nature of the benzoate increases the sigma star CO orbital. This then functions as kind of an electron sink that stabilizes the lactone enolate through an anomeric effect. All of this makes deprotonation at the alpha position of the lactone more likely, which works synergistically with the improved steric accessibility of the inside-out unfolding. Overall, the team developed a really impressive synthesis leveraging the inherent reactivities of the intermediates, and in doing so, also established many new methodologies. Well, that was it for this video. I hope this excursion through the different eras in synthesis was insightful. Thanks a lot for listening and the support. Let me know in the comments what you like best and what other topics you would like to see in the future. Thanks a lot, and until next time.